All right, welcome to one of your last few Friday videos from Met 103. I do sincerely hope that this synchronous 2-day a week and asynchronous 1-day a week has hopefully helped you all a little bit with trying to work your schedules. As I understand, this is turning into a time of year without any breaks that is getting pretty difficult for many. So hopefully this is like a little bit of a way to sleep in maybe for some of you, or if nothing else, change your schedule around just a little bit to be able to take in the necessary material. Today's video here, this first one's going to be a little bit shorter than I thought it was going to be. We were able to work through a lot of precipitation, as you probably remember very well on Wednesday. We had our lab this week that already talked about some of these topics, and so this is not going to be brand new to you as well. Again, please look, I will have another video on to give you a little bit of information on the current homework assignment as well. So we ended off talking about our two precipitation methods, the way that we form it in the warm clouds known as collision coalescence, or CC, and our cold cloud process known as Bergeron-Findyson, or simply the Bergeron or even the BF process. And so when we talk about precipitation type, we're talking about the type of precipitation that, for the most part, what do we see down at the surface? And the first thing is that the majority of this is going to be predicated on the fact that in the mid-latitudes, the Bergeron-Findyson process is going to be the primary way in which all precipitation forms. The question is, what happens then down at the surface? And so do we get rain, snow? Is it sleet or freezing rain, or hail? And so we'll start very briefly actually with the idea of hail. The idea that hail, again, this slide should look very familiar to you, is a little bit different in the sense that we simply have these strong updrafts that are maintaining your precipitation up in a cloud at layers that are below freezing. They're going to be suspended for a period of time depending on the strength of the updraft. And then again, the idea that if you have this tilted updraft, they're going to move horizontally through a cloud as well, continuing to layer. And there still is this idea, though, of the supercooled water that we brought up in the Bergeron-Findyson process. The fact that you have ice crystals and also a large amount, especially in these areas that have these significant updrafts, large amounts of supercooled water because we have such a warm, moist inflow in a thunderstorm environment. And so hail is a little bit separate from what we talk about with a number of the other upcoming features that also are solid as they get down towards the ground. And so again, to reiterate, the vast majority of mid-latitude precipitation is going to be a process or resulting from the Bergeron-Findyson process. Again, that CC process, we're thinking hurricanes, ITCZ, stuff going on much closer to the equator. And so we have a schematic over here on the side that shows, again, this area here in white, which is to indicate that you have sub-freezing air, below zero, and this area in lighter blue that is above freezing. And that's the general idea. And so we already brought this up in lab, what is going on in the vertical profile with the surface being down here in brown. And so again, ice crystals that are up high in a cloud where the precipitation may be forming is going to potentially melt into rain depending on what this subcloud layer looks like. The temperature layer is going to determine that precipitation type, the thickness of the layer that's above freezing. For instance, looking here at the rain profile, it's not too difficult to see. If we simply have a melting here high up in the atmosphere and it remains above freezing down to the surface, we're going to see rain. And so this is what's happening a lot of the time in the summer, and to be fair, the spring and the fall. It may be tens of, or let me say, large number of kilometers above our surface. It may be snow, but it is warm rain by the time it reaches us down at the surface. Other times we see a melting and a refreezing, and then these are going to be the tricky ones. What's happening to form these sleet and freezing rain? Other time, if it is cold throughout the entire atmospheric layer, we're going to simply see snow at the surface. And so snow lovers, it will happen before too much longer. And so here you see the 4 vertical profiles, and this is effectively what you worked on in lab this week. Looking at the simplest profile for rain, or actually I should say the second simplest in some ways, rain here on the right. The idea that you have a sub-freezing layer that melts, it stays above freezing down to the surface, and so the surface experiences rain. Coming over here to A, which is probably, to be fair, the simplest, it starts below freezing. It may warm up, but it never breaches here, this vertical line indicating above freezing. And so it simply says snow throughout the entire layer, and we get the white stuff down at the surface. And so the big two, and the things that are really, really difficult at times for forecasters, is this difference between sleet and freezing rain. And so you can see the big term here. Here in sleet we have a deeper freezing layer. Here with freezing rain we have a much shallower freezing layer. And so again, still starting as snow in both instances. Both freezing rain and sleet we see a melting. But in sleet, it's a pretty quick melting and then a long refreezing to where we get these little balls or white pellets that hit the ground. Here, it melts completely, and it actually may still basically be right around freezing at the surface, but a number of objects at the surface are going to be below freezing. So upon contact, they will freeze with maybe your car, maybe the light pole outside, and under some circumstances when we are below freezing still in air temperature, we may end up seeing this freeze on the roads and the sidewalks and become a very dangerous situation. And this past week, they had areas over 1.5 inches of freezing rain across portions of Oklahoma. Again, I think you could call this definitely a historic ice storm, especially for the month of October. So looking at sleet here again, the idea that here we're breaking it down, getting into a period where it's below freezing. It comes above freezing for an extended period of time, but enough to allow our snowflake to melt into rain. But then there's a deep freezing layer, enough for us to slowly, or sometimes I should say quickly, but gives us enough time for that raindrop to completely freeze back over into little balls. So this is if you've ever been to, say, a baseball game or a amusement park and had those little Dippin' Dots. It kind of looks like those Dippin' Dot ice creams that fall all over the ground. We can see this sometimes in some thunderstorms as well, some little sleet pellets. They may be referred to as grapple if you ever see that word come out. But these are going to be, just kind of rolling around on the ground. They can form some pretty deep layers, and often they will mix with things such as snow or freezing rain. But the key thing is that sleet is refreezing. It hits the surface as a frozen entity. Freezing rain starts again as ice and snow, just like everything else here. It's going to fall into that above freezing air. It's going to have potentially a greater depth of the atmosphere that is above freezing and therefore allowing it to completely melt. And then it has a very shallow sub-freezing layer. Sometimes it can even be barely above freezing at the surface, but we simply have objects that maybe due to nighttime cooling or maybe due to other effects in the atmosphere are slightly below freezing. And we can still get some glazing on some surfaces. Maybe your vehicle, which is made of some type of metal composite, may have some freezing occur on it before a lot of other surfaces. And then, yes, you can sometimes get pictures like what you see here on the side graphic that are just simply catastrophic. Again, freezing rain is probably one of the more dangerous weather conditions we talk about over the course of the semester. But again, the big difference here is a shallow freezing layer versus a deep freezing layer. There's not enough time for our precipitation to refreeze before making it down to the surface. Where do we find freezing rain or freezing drizzle? Again, freezing rain just being a heavier actual falling form of precipitation, whereas drizzle is more of just a mist where you're outside and you can see little particles, but they're just kind of floating around, not necessarily accumulating large amounts at the surface. And so here you can see some very interesting scaling numbers. Again, I don't make the schematics. I'm not quite sure why you go from 10.5 to 15.4, but I digress. Not the greatest graphic, but what you can see here is you have an area over the Midwest, which we see a lot of drizzle. You can see areas down here in Oklahoma are definitely not devoid of freezing drizzle. Not a lot if you're over the southwestern United States, and shockingly Florida doesn't see a whole lot of freezing drizzle, but you are going to see some little pockets here and there. So don't take too much stock on these little white dots. Around here though, we may see 2 to 3 weeks worth of days where we at least see a little bit of freezing drizzle. Ice storms, maybe 1 or 2 times a year. Snowflakes we don't spend a whole lot of time with, to be honest with you, and snowflakes are kind of pretty. But what I want to basically bring up here is that it's a combination of both atmospheric temperature and therefore in some ways the vapor pressure or how much moisture the air can hold that is going to help us to determine what type of snowflake features hit the surface. So you can see that we have ones here at the very cold temperatures referred to as columns A little bit warmer, we have plates. A little warmer, we have dendrites. And then when we oftentimes are getting snow at temperatures just below freezing, we get these needle-like features that hit the ground or hit your jacket and, well, kind of look like flat, pointy features. And so the one of interest to me is the dendrites, the ones that if you ever folded up paper the right way back in kindergarten or first grade and made a few cuts and made a pretty snowflake, or hopefully didn't screw up and have your paper fall apart into 10 pieces, these are what you kind of picture when we talk about the standard or canonical snowflake. Dendrites, we can see temperatures here around this 10 to 15 below freeze, or negative 10 to negative 15 Celsius range. And I talked earlier about this growth zone type setup, and we can get these periods called DGZs or dendritic growth zones, where we can get rapid formation of this type of snowfall. And this is going to be some of these levels that may occur higher up in the atmosphere are going to be prolific snow producers, depending on what the profile of the atmosphere is below the cloud. And so typically we're going to look towards temperatures in the atmosphere somewhere in here for our heaviest snowfalls. In fact, many times we get our heavy snowfalls when it's not too far below freezing, because we need that moisture that we know continues to get lower and lower as it gets colder and colder outside. Snowfall, a slightly better graphic here. You can see if you look around areas like Valpo, 20 to 40 inches of snowfall a year. You do not have to go far away from Valpo. Areas such as South Bend and Benton Harbor in Michigan, again, we don't spend a ton of time talking about the phenomenon known as lake effect snow. But because of our prevailing northwesterly winds to north-northwesterly winds, we actually get notably less snow here in Valpo than we do maybe an hour away in southwest Michigan over the course of a year. But we still do get a good amount of snow. It doesn't mean that Valpo can't get a significant lake effect snow event. It's been a while, so I don't want to say we're due, but maybe this is the year. You can see other areas, though, across the lakes. Again, UP of Michigan, areas over by Lake Erie, especially up here. Areas Buffalo, New York, and areas in upstate New York that can get substantial snowfall year, as well as again in the mountains out in the Rockies. And if you really don't like snow, this probably is not something you needed to learn from Met 103. Head south. That's the way to go. Virga. Virga was something that came up in lab and you hadn't heard about yet, and that's why I warned you up front to make sure you brought your book or other materials. The Google would have been a very easy way to find out what Virga was as well as, let's be fair, your lab professor or lab aides. We know that through our analysis of stability that as you go up in the air, you cool with the dry adiabatic lapse rate until you become saturated at the point where you lift where you reach the lifting condensation level. And so below a cloud base, the air is unsaturated. It may be just barely unsaturated. It may be pretty darn dry. And so there are going to be periods in which you have precipitation forming in a cloud, falling out of the cloud, but before it can reach the ground, it may evaporate. And so you see these wisps in the sky, and we refer to these as virga. In fairness, if you're under a cloud producing virga, you may get a drop, you may get two, but it may look like it's raining much, much heavier above you. This occurs quite commonly when you have high cloud bases and relatively dry conditions near the surface. It's more common as you head west towards the Rockies and get into some of the higher elevations. In reality, virga looks pretty, especially if you can get it in a sunset type scenario. It can be quite dangerous actually for aircraft and things that are flying through, as this can produce some turbulent conditions. We measure precipitation with a rain gauge. It's going to be typically this idea of a tipping bucket, basically this graphic over here on the left. Rain is caught in a funnel. It's a standard size, so we know how much it causes to fall. To fill one of these little buckets, it tips, it hits the sensor, and you can see there's two of these little buckets down here. So as one falls to tip and hit a sensor, the other one then is positioned to catch the next rain. Usually going to measure in increments of 1/100th of an inch. And so every time it hits one of these little sensors, it sends a signal letting the system know that that much rain has been recorded. And this is helpful because it not only lets us know how much has fallen, but the rate at which it falls. In other words, if this is rapidly tilting and falling and tipping and hitting each side, we know that the rate of precipitation is very high. Or if it tips twice in an hour, we know that not only did we only get 2/100ths of an inch, but that we did not get a very rapid rate of precip. We can have other simple ones that actually just fill up in a tube. This is how we measure a lot of the stuff that I've shown occasionally with the CocoRoS data. But we can also measure snow in terms of trying to get the best depth. And snow is a difficult thing to measure. It's not uncommon for people to go out and try to find the drift by their door and say they got 2.5 feet of snow, when in reality they may have gotten 6 inches of snow. And so the general idea behind measuring snow is you find an area that is flat as possible. You measure in a few different locations that are, well, spatially distant to try to get an average of how much snow fell. You want to avoid areas that have either received drifts or had the snow drifted away from, and understanding that when it's a windy snowfall, this can be quite difficult to achieve. The other thing with regard to snow is how much water actually fell during a snowfall. We know that snow falls for every inch of snow, there's not nearly 1 inch of precipitation. It's not a 1-to-1 ratio. So here, if we use a just standard ratio, which, well, to be honest, isn't always the case, we may use a 10-to-1 water equivalent. The idea that 1 inch of liquid water would form 10 inches of snow. And so if you have one of those really wet, heavy to lift snows, you may have had a 7-to-1 ratio, meaning that every 7 inches of snow would, well, melt down to be 1 inch of rainfall. And then other times when it's really, really cold outside and you get the super duper fluffy snow, that may be more of a 20 or 30-to-1 to where we can get a whole lot of snowfall with very little moisture. Other things that we can do are, again, use our Doppler radar capabilities to estimate how much precipitation falls. Again, here we're simply looking at the brightness of the return, or how much of the signal gets returned to our Doppler radar, indicating how much precip, or, well, to be fair, whatever else hail is in a storm. And so we can estimate how much precipitation reaches the surface. Admittedly, this is pretty crude because, again, we may not be measuring the entire depth of a storm. If, for instance, a storm is producing a lot of hail, that may indicate a lot more fell than really did. But it's still a useful tool because we can get a really good spatial coverage. Areas, for instance, maybe out in the Dakotas or Montana where we have very few places that we're actually taking measurements, Doppler radar can help us at least a little bit to determine where some of the heaviest precip may have fallen, and that's going to be particularly useful if we're worried about a flash flooding type event. And so again, we can take this, this is indicating what I was basically just talking about, the idea that we may have a reflectivity up here in the upper right corner, so you can see areas here, we may say have 45 dBz echoes, meaning a little bit heavier rain. Heavier rain is going to be up here. You can see a max here, 54 dBz, and so some spotty precipitation here across Oklahoma. And then over a period of time, here a 1-hour precip, the Doppler radar can give you estimates. So for instance, in some of these areas that we may be seeing the higher echoes, maybe they're not moving very quickly, we have a 1/2 to 3/4 of an inch of precipitation. Now again, this has a tendency in some ways to overestimate how much rainfall. Again, if it's getting reflectivity, for instance, off of hailstones, which are highly reflective, it may significantly overestimate how much precip. And so when we estimate based off of Doppler radar, as best as possible, we're going to try to ground truth that with some of the rain gauge data to try to see exactly how much fell. But again, this can be very useful to give us some idea. For instance, if there were no gauges and this were a very low population area, we may start to really focus in on whether or not this area required some type of warning for flash flooding. All right, folks, that's it. Again, we'll have another video up that helps, if you needed, get through some of the homework stuff. Please bring your questions about the homework to class, and I will also be starting a new topic on Monday. Keep at it, get a little rest, stay healthy. Have a good one.